So here's another exercise involving a right triangle. Suppose that A is an acute angle and that tangent A is 3/4. Find the values of the other 5 trig functions of A. Now, actually, the word right triangle is not mentioned in this problem, but because A is an acute angle, we can draw a triangle that fits the given information. And before I go any further, I just want to repeat this little red statement here. Be sure to compare this to exercise 7 because there's some difference between 6 and 7 where it's really important that you compare the two, and I think you'll see as soon as you look at the two problems together. So here we're going to draw a triangle. We're going to try to draw a triangle that fits the given information where we can make C the 90-degree angle. Here's A, here's B, and now we know tan A is equal to 3/4. We can think of that as the opposite over adjacent ratio from SOHCAHTOA, right? So for angle A, if we could label the opposite side 3 and the adjacent side 4, there we have a right triangle where the tangent of A comes out to be 3/4. And we need to find the hypotenuse, little c, and here we can say 3 squared plus 4 squared is c squared, 9 plus 16 is c squared, 25 is c squared, so positive square root of 25. Here I'm just going to go ahead with the positive square root. We know we're looking for a side of a triangle, so c is equal to 5. And now I'm going to use SOHCAHTOA. Sine A is opposite over hypotenuse, so opposite to A is 3 over 5. Cosine A is adjacent over hypotenuse, so adjacent to A is 4, that's 4 over 5. And we already have tangent A, so we don't need that. We need secant, which is 1 over cosine. So the reciprocal of cosine is just going to be 5 over 4. And we need cosecant, which is the reciprocal of sine. The reciprocal of sine is 5 over 3. And we need cotangent, which is the reciprocal of tangent. So that's going to be 4 over 3. So we got our 3/5, 4/5, 5/4, 5/3, 4/3, and we've solved problem 6. We found the values of the other trig functions for A. think I'm going to go right ahead and do exercise 7 now, right in line. So we want to compare these two. Find the lengths of the missing sides of a right triangle, given that cosine A is 2/3, A is 5, no calculator, side A is opposite A, B opposite B, C opposite C, C is the hypotenuse. So let's try to draw a picture here. Here's angle C, A, B. Now I know side A is 5, so across from A. This is side B. This is side C. And we got cosine A is 2/3. Now, suppose we try to proceed like we did in exercise 6. We know cosine A is 2/3. From SOHCAHTOA, that's supposed to be adjacent over the hypotenuse, right? And so it's kind of tempting to say that the adjacent side to A is 2, and the hypotenuse is 3. So B is 2, C is 3. But now, here's where you can't always do this type of thing. This can't work. This is impossible. And there are different points where you can spot this as you try to work through this problem, but I see it right now because the hypotenuse must be the longest side of the right triangle. And here the hypotenuse has to be C, but we have this other leg being equal to 5. Now that doesn't mean the problem is impossible. We need to proceed differently. We proceed differently. Okay, so it's not like we can't solve it. We just cannot say that C is equal to 3 and B is equal to 2. Now, what we can say is, like, we can use the fact that cosine A is equal to 2/3, and we can say that cosine A has to be equal to B over C, okay? But what that means is, when we put those together, that means that B over C is equal to 2/3. Those two fractions are equal. Saying those two fractions are equal does not mean that B is equal to 2 and C is equal to 3. For instance, B could be 4, C could be 6. B could be 20, C could be 30. So here we'd like to make B 2 and C 3. We just can't because it leads to an impossible situation. All right. So we got B over C equals 2/3. Now that's an equation with two variables. We can't solve for B and C. But we also know, for sure from the Pythagorean theorem that B squared plus 5 squared must equal C squared. That's our Pythagorean theorem relationship. What we have here is a system of equations, of two equations with two variables. So we can actually solve this system for B and C. So we got one equation here, we got one equation here. Both those relationships have to hold in this problem. So it's a little bit more complicated than 6. I'm going to take this equation and I'm going to isolate B. I'm going to take that and multiply both sides by C. So C will cancel. On the left here we get B is equal to 2C over 3. And then I'm going to substitute into that other equation, b squared plus, I'm trying to recopy here, b squared plus 25 equals c squared. Instead of b squared, I write 2c over 3 squared plus 25 equals c squared. A little bit of a mess, but now I can solve for c. So just to recap a bit, we wanted to draw the picture a certain way. It was impossible. So we had to go back and just say the ratio of b over c was 2/3. We didn't know exactly what b and c were. Working with the Pythagorean theorem relationship, we have two equations and two variables, a system of equations that we can solve by substitution. We isolate one variable in one equation, and we substitute into the other equation. And now let's go ahead and start solving this. I got 4c squared over 9 plus 25 equals c squared. I can multiply both sides of that equation by 9. So 9 times 4c squared over 9 plus 9 times 25 equals 9c squared. That allows me to cancel the fraction. 4c squared plus 9 times 25, I have to figure that out. I think that's 225 equals 9c squared. To solve here for c now, I'm going to subtract. I can subtract 4c squared from both sides. And I got 225 equals 9c squared minus 4c squared is 5c squared. I can divide both sides by 5 now. And 225 divided by 5 is going to be 45 is c squared. Another sheet. So I have 45 is c squared. I can take square roots now. 45 is the positive square root of 45 is c. I can factor that 45 is 9 times 5, so I can simplify that square root a little bit into 3. Square root of 5 is c. And that's my c value. Now we still need b. And so I'm going to use that equation in red back here, b, or actually I'm going to use where I have b isolated, right? b equals 2c over 3. I can use any equation that involves b and c, actually from earlier in the problem. So you can go back to an original equation. If you prefer, if that seems easier, that will work just fine. But I'm going to use my equation where b was isolated. And now I'm going to plug in b equals 2 times c is 3 square root of 5. That's what we just figured out. The 3 factors will cancel. So b is 2 square root of 5. And there's my value for b. The sides of my triangle now look like this. That a side was 5, The c side is 3 square root of 5. I couldn't use 3, but 3 square root of 5 works. The b side, I can't use 2, but 2 square root of 5 works. Okay, so we're done, but just notice that cosine of a, if I think of it as adjacent over hypotenuse, if I, just for checking, I have 2 square root of 5 over 3 square root of 5. In that fraction, the square roots actually cancel out. And it checks out that the cosine of a comes out to be 2/3, even though it was far from obvious at the beginning that that square root of 5 would have to be involved. And again, we didn't have to do this extra part. Our answers are in the box to exercise 7. Just put the problem back up here. It was complicated. We got 2 equations and 2 variables, and we ended up solving for b and c.